So we need to find the slope of the tangent line, probably the equation of the tangent line for, we'll say h of x is equal to 3x times the arc sine of x. And we're evaluating this at the point 1/2 pi over 4. Okay, so the first thing we need to do with this problem is we need to use the chain rule. So since we have h of x here, we're going to say h of x is equal to f of x times g of x. This is pretty much a standard for the chain rule. We're going to define f of x as 3x and g of x as arc sine of x. Okay, so the chain rule will be expressed this way. This should be a general rule that you know of, but if you don't, it's basically you take the derivative of one, leave the other alone, and then add the derivative of the other and leave the other alone. So it's kind of a rule. But if we keep going, we'll get that h prime of x, the derivative, is going to be equal to f of x times g prime of x plus g of x times f prime of x. For our case, since f of x is equal to 3x and g of x is equal to arc sine, we will have 3x times the derivative of the arc sine of x plus the arc sine of x times the derivative of 3x. So first, let's figure out how to get the arc sine derivative. So we're going to let y equal the arc sine of x so that we have that sine of y. We're applying sine to both sides, the inverse of arc sine, so that we get sine of y is equal to the sine of the arc sine of x, which will just give us sine of y is equal to x. Once we have this, we'll kind of make a note that the derivative of both sides, taking the implicit differentiation of both sides, will give us cosine of y dy dx. And that'll be equal to dx dx on the other side, on the right side. But dx dx algebraically is just equal to 1. We need to find dy dx, in other words, the derivative of the function. And so if we solve for dy dx, we'll get 1 over cosine of y. Now, the problem here is that we have a function that has a derivative with respect to x, but we have a function on the right side that is of y. So what we'll do is use a Pythagorean identity, one you've probably known about, cosine of y squared plus sine of y squared equal to 1, which means that I can rewrite the equation to solve for cosine of y itself, which will give us the square root of 1 minus sine squared of y. Once we have this, we're still not really finished, but if we remember that at the beginning, we declared that sine of y is equal to x. So then the square root of 1 minus sine squared of y is just going to be equal to the square root of 1 minus x squared. Once we have that, now we have the derivatives, or we have a closer idea of the derivative. The derivative dy dx is going to be equal to 1 over cosine of y, which will be equal to 1 over the square root of 1 minus x squared. And that's for the derivative of the arc sine of x. So now that we have the derivative of arc sine of x, we can go ahead and figure out the rest of the derivative for the problem. What we'll have for the derivative is 3x times the derivative of arc sine of x plus arc sine of x times 3x derivative. Now, the right side is a little bit easier to find. The derivative of 3x is just 3. The derivative of arc sine of x we already figured out was 1 over 1 minus x squared, all square rooted. So we'll have 3x divided by the square root of 1 minus x squared plus the arc sine of x times 3. That's our derivative for our problem. Once we have this, we have our point, which is x equals 1/2 and y equals pi over 4. So then we'll go ahead and plug those in, and we'll say that 3 times x, which is 1/2, divided by 1 minus 1 over 2 squared, which gives us 1/4, and that's the x value, plus the arc sine of 1/2 times 3. So the problem here, as we go further, is what is the arc sine of 1/2? The arc sine of 1/2 basically demands of us to ask, what angle do I get so that sine of that angle is equal to 1/2? So if we look at the unit circle, sine of pi over 6, or 30 degrees, is going to be equal to 1/2. That's part of our special right triangle. If you remember, we have a 30, 60, 90 degree triangle. So our angle here is 30, This is our right triangle. It's not drawn to scale, but the pattern is 1, 2, square root of 3. If we wanted to make the radius, which is the hypotenuse in this case, unit, then we need to divide by 2 everywhere. So we'll get 1 for the radius, 1/2 for the y value. So this will be y, and then x will be in this way. We'll get square root of 3 over 2. So sine of 30 degrees is equal to 1/2. And 30 degrees is pi over 6. So the arc sine of 1/2 is going to be equal to pi over 6. So if we keep going, we can plug that in. We'll get 3 over 2 divided by the square root of 1 minus 1/4. And that will be added to pi over 6 times 3. We can keep going. We'll get 3/2 over the square root of 3/4, 1 minus 1/4, plus 3 pi over 6. Now this reduces, 3 pi over 6 reduces to pi over 2. And we can put the half part, we can put the 2 at the bottom. And we'll go ahead, since we're dealing with real numbers, we'll go ahead and put the 2 inside the square root. So we'll make that a 4. 2 squared is equal to 4, so that we can go ahead and plug that into the square root. Now you'll notice that the 4's will cancel out here. So what we'll get for our derivative, which is also our slope, our m value, slope of the tangent line, the slope will be 3 over square root of 3 plus pi over 2. Now we're not quite done. We need an equation of the line that's tangent to this point. So what we'll do is use the point slope form. Y minus y1 is going to be equal to the slope times x minus x1. Now this slope is shorthand in this case for the derivative, h prime of x. And our point is going to be 1/2 for x and pi over 4 for y. So plugging this in, now I'm not sure what your professor or your teacher may want, but this is technically the correct answer. Y minus y1 is equal to the slope times x minus x1. Okay, now you can simplify this if you like, but this would be it for the particular problem. And our solution to the equation of the line. This would actually represent the equation of the line that's tangent to the point 1/2 and pi over 4. I hope this helped you. Let me know if it does.